Okay, slide 30, so let's go ahead and get started. All right, good evening, everybody. I can officially really say it's evening because it's dark outside, so thanks to daylight savings. So how's everybody doing today? Hopefully everyone had a good Halloween, stayed safe, and hopefully everyone got a good, extra 1 hour of sleep yesterday. Okay. Good, good. Nice, that's good. Okay, so today the plan is we're going to continue our discussion for 2D finite elements. So we're going to go over basically 2D heat conduction. Okay, so we're going to finish up. We're not finish up. We'll continue along with those notes. So the homework was due yesterday, and so I haven't looked at them yet, but I'm hoping to grade them before the end of the week. And then when I grade them, I'll put the solutions up for you guys to take a look at. Okay. So I know it was a long homework, so it was a lot of work. So I appreciate you guys doing that as always, and I'll put up the solutions when I can. And so another announcement I have to make, midterm. So the midterm is not going to be next week, but I think it's going to be 2 weeks from now. Yeah, so the midterm is going to be on Wednesday of week 13. So right now we're in week 11. And so next week we actually have another, the plan is to have another ANSYS activity, but I think what I would rather do is I'd rather get through kind of all the lecture stuff because all the material that is going to be in this lecture notes and the next set of lecture notes, that's going to be everything that's going to be based on your project. So I want to make sure I get all that information to you guys just so you can start working on the project sooner rather than later. So I think we'll probably have the next ANSYS activity either right before the midterm or right after the Thanksgiving break. Okay. And so the other announcement that I wanted to make is the project. So actually, I've made a lot of progress on the project, just in kind of developing the code and writing the specs. And so if you want just a brief look at it, so I can kind of share my screen right here. Okay. And so here's the code. And so I'll just kind of, this top part I don't mind you guys seeing just because it's, this is gonna be the same for everyone. But you can see the code is over 300 lines long, just a quick flyby. And by running the code, you get something that looks like this. Okay? And so what you're going to be solving for is you're going to be solving, basically the 2D heat equation, and you're going to be solving for the temperature distribution in this kind of L-shaped plate right here. Okay. And so you can see the areas that are red right here are hot temperatures, and the areas that are blue here are cold temperatures. Okay? So you have this kind of interesting distribution. Right? And it's going to bring together basically everything that we've learned about finite element form. So you're going to be deriving element stiffness matrices, deriving element forcing vectors, applying boundary conditions, both Dirichlet and Neumann boundary conditions, and then solving for the solution. Okay? And so you're basically going to be writing up like a mini ANSYS code yourself. So if you're ever wondering how ANSYS is implemented on the inside, you're going to get a good look at for this project. Okay. Yeah, you can mesh in MATLAB. Yeah, so I think you guys need to install a certain package, but I'll walk everyone through that once we get there. Okay? And so the next question is it time variant? So the answer is no. So it's going to be a steady state solution. So there's going to be no time derivative to it. So it's basically going to be exactly the equation that we're going to go over today, but just you're going to be implementing it within MATLAB. Okay, and here's kind of the result. Okay. Actually, if you want to see the mesh, let me run it again. And so the mesh looks something like this. Okay. And so basically where the challenge for this project is that the mesh is going to be generated fairly arbitrarily. And so you're not going to know, first of all, there's a bunch of elements here that you can see, and you're not going to know the coordinates for each of these elements, a priori. And so you're going to need to write your code such that it's kind of generic for any kind of element. Yeah, and so I'm, once the project drops, so I think probably on Wednesday, I'll spend a bit of time to talk about, how to mesh in MATLAB. So I'm going to write that code for you because it's, I'm using some kind of some advanced MATLAB packages, but I'll basically show you how to do it. So if you want to do kind of your own project with this, outside of this class and mesh some certain geometries, you can use this package for that as well. But yeah, we'll walk through all of it. So the meshing, I think, is I think probably a lot of you haven't used it because that uses the PDE framework within MATLAB. But then from there, we'll the rest of it you should be able to implement yourself. Okay? Yeah, so the midterm is going to be in 2 weeks. So the midterm is going to be in week 13, so not week 12. And so right now, yeah. So the midterm is going to be in Wednesday of week 13, so 2 weeks from Wednesday. Yeah, so it's going to be right before the Thanksgiving break, basically. So I'm going to have you guys take the midterm right before Thanksgiving. I'll grade it over Thanksgiving, and then you'll have your grades by then. Okay. Okay, so any questions on this or any questions on the project or anything that I can answer before we get started? Okay, so let me reconnect my iPad here. So the final project isn't available yet, so I still need to type up the formal documents for it. But it will be available starting on Wednesday. Okay, and I think the due date that I've set for the finals is going to be the Monday after finals week. So basically, right before Christmas, it's going to be due because I know that you guys have other finals to study for during finals week, and with the project, you know, we can be a little bit more flexible on the due date. The only thing is I have to grade it before grades are due. And so I want to give you until, you know, a little bit after finals week. So at least you have that weekend if you needed to work on the final project. And so of course you're welcome to submit it beforehand, but you know, I'll give you until the Monday after finals week just to give you guys a little bit extra time. It's going to be quite a bit of code development too. So I think, you know, it's going to be quite a lot. Okay. So that's a preview of the project. So I'll have the specs and all the starter code ready for you guys on Wednesday. So, you know, and we'll discuss it then. So we'll discuss, you know, the meshing and what you have to install for MATLAB as well, okay? But for today, we're going to continue our discussion for 2D finite elements, okay? And so I think the last thing that we covered last time was the weak form for 2D heat conduction, okay? Okay? And so the expression for that looks like this, okay? So we have a double integral, because we're in 2D, okay, of the gradient of our weighting function, W, dot product with K, gradient of T, okay, a dA, right? And so this right here, remember this is a term that comes out of our Green's formula. And so this right here is our balanced derivative integral. Okay. And just a preview for what's coming today, this integral right here will form the basis for our element stiffness matrix. Okay. And so this is going to be equal to minus a line integral of W times Q times ds. Okay. And so this integral right here, this is our Neumann boundary condition. Okay. Because remember, whenever we have a weak form, you know, any Neumann boundary conditions are going to be baked into our expressions. We don't need to do them separately, you know, like we usually do with the strong form. Okay. And this is going to be equal to our double integral of our weighting function multiplied by our heat generation. Okay. So our heat generation term is a function of x and y. Okay. It's going to be dA. And so this is our heat generation. Okay. Let me rewrite this to be a little more clear. And so it's W multiplied by S of X and Y dA. Okay. And so these guys in combination, the Neumann VC and the heat generation term, these guys will make it into our element forcing vector. Okay, so just like in our 1D case. Right. And so that was that's kind of where we left off on last time. Okay. Okay, so the question in the chat is, what do I mean by a balanced derivative? Yeah, it's a great question. And so remember remember when we did 1D cases, when we multiplied by our weighting function, and then we multiplied that by the second order derivative on the temperature, we had this kind of unbalance of derivatives where our weighting function had no derivatives, and then our temperature derivative, our temperature term had two derivatives. Okay? And so the way that manifests in 2D are the fact that we have, these two terms right here. Okay? And so, for our weighting function, we have a gradient operator that's applied. And so you can kind of think of the gradient operator as like a first order derivative term. And then the gradient operator on the temperature is also a first order derivative. And so when I say it's balanced, what I mean is that it's balanced between the weighting function and the temperature. And the reason we did this, or the way that we achieved this, I guess, is we applied integration by parts. And then with integration by parts, we're able to move some of the derivatives around to the different functions. Okay? And the reason we did this, remember, is so that we could, lessen the continuity requirements for our solution. Okay? Because when we only have first order derivatives, okay? And so when our governing equation only has first order derivatives, what this means is that the shape functions that we can use, or the assumed approximate solution, can be a linear function. Okay. And linear shape functions are really, really nice because they're a lot simpler than quadratic. Okay? And so if you had a case where the derivatives weren't balanced, so let's say that we had, instead of nabla t, or the gradient of t, we had the Laplacian, so nabla squared t. And so if this were the case, if we had a term that looked like this, our shape functions have to be quadratic. Have to be at least quadratic. And in those situations with the quadratic shape function, you really, increase the amount of work that you do really significantly. Okay. Okay. And so what we're going to do today is we're going to take this weak form, and then we're going to see how we can turn this into a finite form. Okay. All right. Any more questions on this before I move on to the next page? So one nice bit of trivia about this is that even though we're going over this as the heat equation, this equation actually can work for any kind of scalar transport. So if you've ever taken a class in like mass transport, mass transport follows this exact same equation. So most of the time you'll see this described as the heat equation, just because that's the most recognizable name. But sometimes you might see it described as like the scalar transport equation, and they both kind of mean the same thing. Okay, so that was the weak form. And so just like we did for the 1D problems, we can take our weak form, and then from there we can derive our finite element form. Okay. And so this is going to be the finite element form for 2D heat conduction. Okay. Okay. And so for finite element forms, we basically are going to follow the same process that we followed, before for finite elements. Okay. And so if you remember from the first midterm and from the very first, class, there's a method, or there's a process in which we follow to develop finite element forms. Okay. And so the first step, in finite element forms is to discretize our domain into finite elements. Or in other words, this is meshing. Okay. And so let's say that we have an amorphous blob here for our domain. Okay. Okay. So this is our 2D domain. Okay. And then if we want to discretize it, it will look like this. And so we'll have the same amorphous blob, but instead of being just one blob, we're going to split this into a lot of smaller blocks, okay? And so one way that you can do it, just because it's easy to draw, is just to put, squares everywhere. Okay? And so what you have right here is something that looks like a waffle, right? And so this is one way to discretize a domain, okay? Another way to discretize a domain is just like, the project that I showed you. So instead of filling this domain with quadrilaterals, we can instead fill them with triangles, okay? And that, gives us one of the huge complications that you'll see in 2D finite elements over 1D, okay? And so in 2D, we can pick the element shape. Okay? Because in 1D, you really only had one choice. So the only shape that you can have for an element in 1D was just a small line, okay? And so in 2D, you can basically use any kind of 2D shape that you can imagine as your element shapes, okay? Obviously, there's some shapes that work better than the other ones, okay? And in particular, for this class, we're gonna go over the two most common shapes, both of which you can find in ANSYS, right? And so the first shape that we'll go over is the triangle, okay? And the next shape that we'll go over is the quadrilateral. So the quadrilateral is just a fancy term for a rectangle, okay? And so we're going to go over both of those elements, over the course of this week, and we'll see how they become, element stiffness matrices, okay? Okay. And so, before we move on to the shapes, I do want to mention that, even though we're in 2D, we still have the same requirements on our finite element solution. Okay, so if you remember, kind of back when we went over finite element forms in 1D, we said that the solution to our finite element problem has to be continuous along over the element boundaries. Okay, and so what that means is that if you jump from one element to the other one, okay, then the solution can't jump. So it has to be kind of a very smooth curve over the 2D over the element boundaries. Okay. And so this idea of a boundary is going to be, more generalized here because, now we have an edge. But so if you travel across an edge, your solution can't make a big jump. Okay. And so the other requirements that we went over was continuity and completeness. Okay. And so I won't go over them, explicitly again, just because, they're not, too relevant, or they're going to be kind of implicitly satisfied by, the shape functions that we choose. But I just want to kind of remind you, that 2D finite elements satisfy these. And because, we went through the trouble of doing the integration by parts, we can use linear shape functions for this. Okay. And the fact that we can use linear shape functions means that, we have a big smiley face, because linear shape functions are really nice. So I'm not even going to get into quadratic shape functions for 2D finite elements because, it's going to be a huge mess. So even with linear shape functions, you can see it's still going to be a mess, but it's going to be much less of a mess than if we did a quadratic shape functions. Okay. Okay. Any questions on this before we jump into the triangular element? Okay. Okay, and so let's start going into the different element types. So let's start with the triangle. And so if we use linear shape functions and we have a triangular element, then this combination basically gives us what's called the 3-node triangle. Okay. And so just like the name suggests, we have a triangle, and this triangle has 3 nodes. Okay? So we're basically going to have one node at each of the vertices of the triangle. Right, so I'm going to number these nodes, somewhat arbitrarily, but you don't have to choose this numbering. But this is just this kind of a standard way. Okay? And so for location 1 right here, location 1 is going to have coordinates x1 and y1. Okay? Location 2 is going to have coordinates x2 and y2, and then location 3 is going to have coordinates x3 and y3. Okay. And then also at these nodes, since we're solving, the heat equation, each of them are going to have a corresponding nodal solution value too. Okay. And so we're going to have a nodal solution value of T1 at node 1. At node number 2, we're going to have T2. And at node number 3, we're going to have T3. Okay. And so this is kind of our generalization of our 1D element, except now we're in 2D and we have both X and Y cases. Okay, and so let's follow basically the same process that we follow for the 1D case, okay, which kind of follows along with our finite element method. Okay, and so now that we've established our domain and we've discretized it, the next step is to assume a functional form for the solution. And so, what this functional form basically will allow us to do is it will allow us to interpolate the solution across the element. Okay? And so another name for this functional form is the interpolation function. Okay. And so since we have 3 nodes in this system, okay, 3 nodes means 3 nodal solution values. And so what this means is that our interpolation function, it can have 3 unknowns. Okay. Okay. And so we'll denote this function as TE. Okay. Okay. And it's going to be a function of X and Y. Okay. And 3 unknowns means that we can have 3 coefficients here. Okay. Okay. And so we're going to have A1 or A0, A1, and A2. Okay. Oops. And then since this is a linear function, I'm going to put an X next to A1 and a Y next to A2. Okay. And so what this function basically says is that we have a constant term, so that's A0. We have a term that's linear in X, so that's A1X. And we have a term that's linear in Y, so that's A2Y. Okay. And so just like we did in the 1D case, we're going to solve for all the coefficients. So solve for A0, A1, and A2. Okay. And the way that we're going to solve for them is that we're going to require that our interpolation function matches the nodal solution values. Okay. Okay. And so what we're going to have on the next page is a system of 3 equations and 3 unknowns to solve for A0, A1, and A2. Okay. All right. Any questions on this before I turn the page? Okay. Okay. So let's write our system of 3 equations. Okay. And so the first one that we have is we have to match the solution at node 1. Okay. And so what we can say is that T at E at coordinates x1 and y1. Okay. Because remember, those are the coordinates for the node number 1. Okay. And then if we're at that location, then our temperature solution has to be T1. Okay. Okay. And then there's our our function value there, okay? And so we can say that T1 has to equal to A0 plus A1x1 plus A2 y1. Okay? Okay. And so we can write a similar equation for node number 2. Okay. Okay. And so that second equation there requires that our interpolation function matches the nodal solution at node number 2. Okay. And then finally, we can have the same expression for node number 3. Okay, so we have TE at x3, y3 has to equal T3. Okay. Okay. Right. And so here is our 3 equations for our 3 unknowns. Okay. Okay. And so I'm not going to solve for this, but in theory, you could solve for it, right? So it'll be a big exercise in linear algebra. Okay. Okay. And then what we get from this is an expression that looks like this. Okay. And so after we plug in for A0, A1, A2, okay, then we can put the solution in this form. Okay, so we can have T1 times N1 of x and y. Okay, where N1 of x and y, remember that's our shape function. But now our shape function has x and y variables. Okay. Okay. And so same thing for T2. And so T2 is going to be paired with its own shape function, N2. Okay. Okay. And then we have the same term for N3. Okay. So we have T3, N3. Okay. And so the values of the coefficients, they're kind of baked into these guys. So I haven't not for a long time, I haven't solved for the exact values of that. But once we solve for those coefficients, we can basically rearrange the equation and put things in terms of shape functions. Because these shape functions are going to be really valuable for us as we form our element stiffness matrix. Okay. All right. So let me give you the formulas for the shape functions, because that's going to be the most important. And so we have N1 of x and y. So this is going to be 1 over 2a. Okay. And so a in this case is the area of our triangle. Okay. And so this is going to be x2, y3 minus x3, y2 plus y2 minus y3x plus x2 minus x3y. Okay. So that's N1. Okay. N2 of x and y is going to have a similar expression. Okay. And so again, we start out with 1 over 2a. Okay. And it's going to be times x2, x3, y1 minus x1, y3 plus y3 minus y1 x plus x1 minus x3 y. Okay. And I just realized I made a small typo up here. So this should be x3 minus x2 up here. Sorry about that. So I made a correction for N1 on the very last term that's multiplied with y. So originally I wrote x2 minus x3, and so that should be x3 minus x2. Yeah. All right. So the question is, are these like an algebraic distribution from somewhere? I think so. I think these are probably derived from like a 2D Pascal's triangle, something like that. Because you're right, there is a pattern to this. And I think that it might be Pascal's triangle, but I'm not sure. But I think they are derived from some algebraic distribution. And then finally, we have n3. And so we have n3 of x and y is equal to 1 over 2a. Okay. And this is going to be multiplied by x1, y2, okay, minus x2, y1, plus y1 minus y2, x, plus x2 minus x1, y. So I know I wrote this kind of messily right here, but it's a lot neater in the lecture notes. So this is going to be page top of page 7 of the lecture notes. So you should be able to read it, more clearly. Okay? And remember that A, this is the area of the triangle. Okay. And so those are our shape functions. You can see they're pretty complicated here in 2D because we have those 2 different coordinates now instead of just 1. Okay. Okay. And so that was quite a doozy. And so probably still people are writing it down. So are there any questions I can answer on this page before we move on?
Professor?
Yep.
And the n2, the last part is x1 minus x3?
Yes. Yes. Yeah. So this is the last term is x1 minus x3 times y. Make this a little bit neater. Okay. Any more questions on this page right here? Okay. Okay. And so those are the shape function values, okay, or the shape function expressions. But one other thing that we're going to need before we, actually form the weak form is we need the derivatives of this guy. Okay. 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 So let's write these out. So we're actually going to have 6 of these, right? And so we have 3 different shape functions here. So we have n1, n2, n3, and we can take the derivatives of them in either the x direction and the y direction. Okay? So there's actually quite a lot here. Okay? And so let's start writing it down. Okay? And so first we have partial n1, partial x. Okay? Okay? And so if we take the derivative of n1 with respect to x, then we get y2 minus y3, okay, all divided by 2a. Okay? Then we also have partial n2, partial x, and so this gives us y3 minus y1 all over 2a. Okay? And finally, we have partial n3, partial x, so this is y1 minus y2 all over 2a. Okay? Right. So that's all the x derivatives, and so now we can do the y derivatives. And so if we have partial n1, partial y, then we have x3 minus x2 all over 2a. Okay. If we have partial n2, partial y, this is equal to x1 minus x3 all over 2a. Okay. Okay. And then we have partial n3, partial y. Okay. And this is going to be x2 minus x1 all over 2a. Okay. And so those are all the shape function derivatives. Okay? So when you're solving for the element stiffness matrix for 2D triangles, you need to invoke these guys. Okay. And so what you'll notice, for 2D finite elements, maybe it's bringing back some memories from the frame equations. It's a lot of really tedious calculations. So by themselves, a lot of these are just arithmetic. So we're just taking subtractions and we're taking divisions. And so by themselves, they're not terribly complicated calculations. But there's just a lot of them. So the difficulty just comes in the volume of these calculations. Okay. Okay, and so those are the shape function derivatives, right? And so now remember, the reason we did this is so that we can plug these guys into the weak form. Okay. And remember, in the weak form, or at least in that first integral that we had, remember we had gradient of w, and also gradient of t. Okay. And so in order to actually compute these, we're going to use these shape functions along with a weighting function and our t function. Okay. And so the weighting function that we're going to plug in is going to be a function of x and y. Okay. It's going to be w1 and 1 plus w2 and 2 plus w3 and 3. Okay. And then t of x and y is going to have a similar form, which we've already seen. I'll write it again here for clarity. Okay. And so those are our functions. Okay. So this is very similar to what we did in 1D, but now we're extending it to 2D. Okay. Okay. And so let's actually write out the expressions for this gradient. Okay? So I'm going to start with the gradient of t. Okay. And so gradient of t is going to be we're going to have derivatives in both x and y. Okay. And so, the way that we can express this is in vector form. So that's why I have this kind of vector arrow on top. Okay. And so partial t partial x is going to be t1 times d partial n 1 partial x. Okay. Plus t2 partial n 2 partial x plus t3 partial n 3 partial x. Okay. Right. And then on the bottom, for partial t partial y, we have t1 times partial n1 partial y plus t2 partial n2 partial y, okay, plus t3 partial n3 partial y, okay. And so that's our vector expression for that, okay. And so usually in this form, it's a little bit cumbersome to write down, and it's also a little bit inconvenient to write out the full element stiffness matrix. And so I'm going to put this in a little bit more compact form on the next page. Okay. Okay. Are there any questions on this before I move on? Okay. Okay. And so the more compact form for del T is given by the following. Okay. And so we express it as a product of these two matrices. And so in the first matrix, we're going to have all of our shape function derivatives. Okay. So we have partial n1, partial x, partial n2, partial x, and then partial n3, partial x. Okay. Okay. And on the bottom, we have partial n1, partial y, partial n2, partial y, and then partial n3, partial y. Okay. And then on the right here, we have our temperature vector. Okay. And so we have T1, T2, T3. Okay. And so if you perform the matrix multiplication between these two vectors here, you can see that we'll get the same expression for on the previous page. Okay. And so we can get a similar expression for W. Okay. Okay. And so that expression looks like the following. And so for the gradient of W, we actually invert it a little bit just so that it's easier for us to compute element stiffness. Okay? And so grad W is going to be W1, W2, W3, okay, as a row vector. And then to that, we're going to multiply our shape function derivatives. Okay? So we have partial N1, partial X, partial N2, partial X, partial N3, partial X, okay, and partial N1, partial Y, partial N2, partial Y, partial N3, partial Y, okay? And so you can see, you know, this the shape function derivative that I have on the right is the same as this guy, except it's just transposed. So we basically transpose the shape, the weighting function, just to make things just a little bit more convenient. Okay, and so once we have these, we can plug it in. Plug this into our integral with our balanced derivatives. Okay? And so just to remind you, the integral looks like the following. And so we have double integral of the grad W, okay, multiplied by K times grad T, okay, dA. Okay. Right, and so grad W is going to go right here, and then grad T is going to go over here. Okay. And so what we'll get in the end is basically the multiplication of these two shape function matrices right here. Okay. Okay. And then by multiplying these two, what we're going to end up with is a 3x3 element stiffness matrix. Okay. And so I want to mention that now, just because once we get to the next page, it's going to be a lot of calculations, and so I don't think I'll even be able to fit it on this iPad. But I'll do my best, and I'll write out the whole thing just because it's important. Okay. Okay. Any questions on this before we jump to that? Okay. Okay. And so when we plug in our expressions for grad W and grad T, we're left with the following. Okay? And so first we have our coefficients W1, W2, and W3. Okay? And so those guys are constants, so we can just pull them out of the integral. Okay? Then we have our shape function derivatives. Okay? Okay? And so those are the derivatives with respect to x. Okay? And those are the derivatives with respect to y. Okay? Then to that, we're going to multiply by k. Okay? And then we have our shape function derivatives again. Okay? This time from the t term. Okay. Okay. And then to this, on the right-hand side right here, we have T1, T2, T3. Okay. And so all I did to get this expression was I just plugged in my formulas for grad W and grad T. Okay. Okay. And so you can, if you kind of remember from our 1D case, okay, once we get it in this form, we basically just cancel out these shape functions or these weighting terms, okay, because we don't care. Okay. Okay. Because remember, our weighting function was just an arbitrary function, and really its only purpose was to help us lower the order of the derivatives for our expression. Okay. But we don't actually care to actually solve for it. And so what we actually care about are these guys, okay? T1, T2, T3, okay? And so to help us with that, you know, what we have in the middle right here, this is going to be our element stiffness matrix. And the way that we get a matrix from this is we're going to perform a multiplication in between this matrix and this matrix. Okay? And so this matrix is 3 by 2. This matrix is 2 by 3. And so when you multiply them together, then you get a 3 by 3 matrix. Okay. And so right now I'm just stalling because I don't want to write out this entire thing, but you know, it has to be done eventually. Okay, so I'm going to write out kind of basically the result of if you multiply this matrix 3 by 2 by this matrix 2 by 3 right here. Okay. All right. Yes, so we can take out T1, T2, and T3 out of the integral as well. But those don't cancel out because, you know, once we combine this with the Neumann boundary condition term and the heat generation term, you know, the T1, T2, T3 are what we can actually solve for. But, you know, if you kind of remember from our 1D case, then all three of our integrals here, all three of our terms have this W1, W2, W3. Okay. And since it's present in all of the, both the element stiffness matrix and the element forcing vector, we can just kind of cancel them out. But yeah, in this case, T1, T2, T3 are also constants and they're also taken out of the integral. Yeah, okay. Okay, so here's our element stiffness matrix. And so we have double integral, okay. So we have K. Okay, and so we have this 3 by 3. So it's not going to look like a 3 by 3 because it's going to be a bajillion terms, but it's a 3 by 3. Okay, so then first we have partial n1 partial x times partial n1 partial x, okay, plus partial n1 partial y partial n1 partial y, okay. And so next we have partial n1 partial x partial n2 partial x, okay, plus partial n1 partial y partial n2 partial y, okay. And in this last term over here, we're going to have partial n1 partial x partial n3 partial x plus partial n1 partial y partial n3 partial y. Just barely ran out of space there. Okay. Let me do this. And so this last term over here is going to be partial n1 partial y partial n3 partial y. Okay. Right. And so that's the first row in the matrix. Right. And so the next two rows, they're going to be, you know, the same. Okay. And so I'm going to invoke, you know, the kind of the thing that we did before. Okay. And so I'll say that this this matrix is symmetric. Okay. And so what that basically means is that this this term right here, okay, the term that's in the 1-2 slot is going to be the same as the term in the 2-1 slot. Okay. Yes, it's symmetric. And then also the term in the 1-3 slot is going to be the same as the term in the 3-1 slot, which is right here. Okay. Right. And so I'm only going to draw basically the upper right half of this matrix. Okay. Okay. And so in the 2-2 spot and on the diagonal, we have partial n2 partial x partial n2 partial x plus partial n2 partial y partial n2 partial y, okay. And over here we have partial n2 partial x partial n3 partial x plus partial n2 partial y partial n3 partial y, okay. And also just like with symmetry, then this guy is going to be the same as this guy. Okay. Okay. So that's 1, 2, 3, 4, 5, 6, 7, 8. And so the only term that we're missing is the guy here in the bottom right. And so in the bottom right, we have partial n3, partial x, partial n3, partial x, plus partial n3 partial y partial n3 partial y. Okay. Okay. So it's a doozy. So it's a lot of calculations, a lot of multiplications, and a lot of adding. Okay, and they all involve our shape function derivatives. Okay, and so doing these by hand is going to be a huge pain in the butt because you have to do all these calculations manually. But with the programming language, what you'll see is that if you can leverage basically the matrix multiplication in MATLAB, this is actually a lot simpler to do in code. Okay. Right. Yes. So remember, matrix multiplication is not commutative. So you want to make sure that you kind of maintain the same order of operations as in the original equations. Otherwise, you're not going to get the right results. Yeah, that's really important. Okay, and so that's the element stiffness matrix for a triangle. Okay, and so don't remember also that there's also a K out in front here. He's often forgotten. Okay, and there's also a dA that's on the right over here too. Okay, and so what we're going to do, after I write out the element forcing vector, is we're going to compute one of these by hand. And you need to make sure that you remember the K and you remember the area as well. Okay. But before I do that, are there any questions on this page here? Okay, and so let's write out the element forcing vector. Okay. And so remember, our element forcing vector is going to have two contributions. And so we're going to have one contribution from the Neumann boundary conditions and also one contribution from the heat generation. All right, so the question in the chat is what happened to the T1, T2, T3? So yeah, they're still there. I just ran out of room to write them. So they're still out there on the right-hand side. Yeah. Okay. And so first, let's do the Neumann boundary condition term. Yeah, so for the lecture notes, I'm constrained because my iPad is tiny, but definitely keep reference with the posted lecture notes, because that's even on the lecture notes I ran out of room, but at least I could kind of write it in. Okay. But definitely cross-reference with that, because I know my writing on the iPad is not the best, so definitely check that out when you get the chance. Okay, so for the Neumann boundary condition term, that integral looked like this, and so we had the line integral of W q bar ds. Okay, and so if we plug in our expressions for W, then we get the following. Okay. Okay, and so we have minus W1, W2, W3, okay, integral of our shape functions. We have N1, N2, N3, okay, times Q ds. And so just like we did on the previous side, because we have a W that's present in every single one of these terms, we can cancel them out. Okay. Okay. And then we also have our expression for heat generation. Okay. And so this is going to be double integral of W times S dA. Okay. And so if we plug in for our expressions here, we have W1, W2, W3, okay, multiplied by double integral of our shape functions, N1, N2, N3, okay, times S of X and Y, dA. Okay. And then we're also going to cancel out this W1, W2, W3. Okay. And so our element forcing vector, thankfully, is a lot more compact than our element stiffness matrix. Okay. Is going to just be the sum of these two guys. Okay. So we have line integral of N1, N2, N3, okay, times Q bar ds plus double integral of n1, n2, n3, s of x and y, dA. Okay. Right? And so a lot more compact because we don't have to deal with any derivatives. Okay. And so if we put this all together with our element stiffness matrix, then we can get our elemental system for the 3-node triangle. Okay. Before I do that, are there any questions on this? Okay. And so we put this all together, then we get KE, which is our element stiffness matrix, which was our big monster with all the shape function derivatives, times the temperatures. Okay, so we have T1, T2, and T3, and this is equal to FE. And so this right here is our elemental system. Right? So it's a lot. So I know. So and so we're going to do an example next to show you just how tedious these calculations can be once you're doing them by hand. So the project actually is even though the project is going to be a lot of work, what you'll see is that the computer really speeds things up, and MATLAB really helps you out with these calculations, because otherwise you're doing these by hand. You're going to be doing this forever. Okay, so let's do an example. Okay, and so let's say we have the following 2 elements. Okay, or let's just do one of the elements. Okay, and so let's consider the following triangle. Okay, and so let's get or hang on. Okay, so the coordinates are the following. Okay, so we have a coordinate here, and so this is node number 1, and so we'll say this is 0, 0. Okay, and so node number 2 will be up here, and the coordinates for 2 are going to be 1, 2. Okay, and then finally we have node number 3 over here. Okay, and the coordinates for this are going to be 2, 1. Okay. Okay, and so given these guys, let's compute the element stiffness matrix for this element. Okay. Okay. And so, in order to compute this element stiffness matrix, we need to form the shape functions. Okay. And for the shape functions, we need 2 things. We need the coordinates for all the vertices, but we also need the area. Okay. Oh, so node number 1, the coordinates are 0, 0. Yeah. Mm-hmm. So it's basically just the origin. Mm-hmm. Okay. All right. So we need nodal coordinates. And we also need the area. And so the nodal coordinates are already given to us, and so we can put a check mark there. And area we can actually compute from the nodal coordinates as well. Okay. And so if you're given a triangle in terms of its xy coordinates, there's actually a formula that you can use to compute the area. Okay? And so the area is going to be given by the following. And so area is 1/2 times x1 times y2 minus y3, okay, plus x2 times y3 minus y1 plus x3 times y1 minus y2. Okay. Okay. And so this is a formula for area of a triangle. From the coordinates. from coordinates of the vertices. Okay. And so this is a formula that you can look up like online or something. Okay. And so we plug in the values for, you know, x1, x2, x3, y1, y2, y3 for this triangle. And then what we get is an area of 1.5. Okay. Okay. Oh, and one thing I forget, so I always forget this. We need our thermal conductivity. And so for this problem, let's assume a thermal conductivity of 6. Okay. And so now that we have the area, we have the thermal conductivity. So the next step will be to compute the shape function derivatives. Okay. Okay, so before I do that, are there any questions on this? Okay. Okay, and so let's compute our shape function derivatives. Okay. And so remember, we're going to have 6 of them. And so we need to take the derivative of all 3 shape functions with respect to x and y. Okay. And so let's start with the partial n1, partial x. Okay. And so remember, this is going to be y2 minus y3 all over 2a. Okay. And so we plug in the numbers, what we get is 1 over 3. Okay. Okay. Then we have partial n2, partial x. So this can be y3 minus y1 all over 2a. Okay. And so this is going to be 2 over 3. Okay. Right. And we have partial n3, partial x, which is equal to y1 minus y2 all over 2a. Okay. And this is a minus 2 over 3. Okay. Right, so those are all the x derivatives. So now let's compute the y derivatives. And so partial n1 partial y is going to be x3 minus x2 all over 2a. Okay. And so this is going to be 1 over 3. Okay. Okay. Then we have partial n2 partial y. And so this is going to be x1 minus x3 all over 2a. Okay. And so this is going to be minus 2 over 3. Right. And then finally, we have partial n3 partial y, which is going to be x2 minus x1 all over 2a. And this is a positive 1/3. Okay. Okay. And so those are our shape function derivatives. Okay. And so now that we have all these, now comes the fun part. Is to plug in to our expression for the element stiffness matrix. Okay. Okay. And so this next part, you know, you can write these down if you want, or you can just watch me write all these down because it's going to be a lot. And so remember, in the lecture notes, this is a lot more neat than what I'm about to write now. But you know, it's I'm going to basically do my best here. Okay. But you know, I think writing these down and trying to follow along, you know, I think is you know, I would recommend just watching. Okay, so I'm not going to write out the whole formula for the element stiffness, but I will show you what it looks like after you plug it all. Okay. And so this is just the term with the shape function derivative. So we still need to multiply by k and af. Okay, so remind me to do that. So don't let me forget. Okay. Okay, so we start in the top left, and so in the top left we have 1/3 which is dn1 dx times 1/3 plus dn1 dy, dn1 dy. So that's going to be 1/3 times 1/3. Okay. And so next right here we have dn1 dx and then dn2 dx. Okay. And so this can be 1/3 times 2/3. Okay. Plus dn1 dx or dn1 dy and dn2 dy. Okay. And so this can be 1/3 times minus 2/3. Okay. Okay. And then finally, in the top right here, we have minus 1/3, which is dn. We have positive 1/3, sorry, which is dn1 dx, and then we have a minus 2/3, which is dn3 dx, and then we have plus a minus a positive 1/3, and then a positive 1/3. Okay. Okay. And so I'm going to be cheap again. I'm going to say that this is symmetric, so I'm not going to compute the all of these guys. But remember that, you know, because of symmetry, you know, this guy is going to be equivalent to this guy, and then this guy is going to be equivalent to this guy. Okay. Okay, so now let's write out the diagonal. So that's going to be dn2 dx squared. So that's going to be 2/3 times 2/3. Okay. Plus minus 2/3 times minus 2/3. Okay. And so that's dn2 dx squared plus dn2 dy squared. Okay. And then we have the term out here. So it's going to be dn2 dx, which is 2/3. Okay. And then dn3 dx, which is minus 2/3. Okay. Plus dn2 dy, which is a minus 2/3. And then dn3 dy, which is a 1/3. Okay. And so same thing here. So we're going to say that this guy is equivalent to this guy. Okay. And then finally, we have the term in the bottom right, which is dn3 dx squared. So this is going to be a minus 2/3 minus 2/3. Okay. Plus dn3 dy squared. So it would be 1/3 1/3. Okay. Right. So it's a lot of plugging and chugging. So it's you know, it's a lot. So you know, if when you're doing these problems by hand, definitely take your time, because there's a lot of room for kind of small arithmetic errors, which I make on a constant basis. So you know, definitely take your time with these and make sure you're plugging in the right variables. Okay. Are there any questions on this before I finish up this example? Okay. Okay, and so once we perform all of the arithmetic and all of the multiplication, then what we get is a matrix that looks like this. And so we have 2/9, 0, minus 1/9, 0, 8/9, minus 6/9, minus 1/9, minus 6/9, and then 5/9. Okay. Right. And so that's the matrix after we perform all the arithmetic of the shape function derivatives. But remember, we're not done yet. Okay. Because remember, what our expression was for the element stiffness matrix was this. Okay? And so we had double integral of k times this matrix here. Okay. Multiplied by dA. Okay. And so since both of these guys are constants, right, there's no function of x or y here. We can pull that out of the integral. Okay. And so what we get is k times our matrix. times the double integral of dA. Okay. And since we're just integrating dA right here, this guy just turns into the area, which is A. Okay. And so what we have here is our 3x3 matrix, which we got from the shape function derivatives, multiplied by K and multiplied by A. Okay. And so just by the magic of me picking the numbers to be nice here, the product of K and A in this case, remember K was 6 and A was 1.5. Okay. And so the product of these guys is going to be 9. Okay. And so by magic, this 9 is going to cancel out with the all the denominator there. Okay. And so what we get finally for our element stiffness matrix is just 2, 0, minus 1, 0, 8, minus 6, minus 1, minus 6, and 5. Okay. Right. So when I was writing this example, I totally didn't change K to 6 so that everything works out nice. Right? But in reality, you're not going to get an element stiffness matrix that works out this nicely. But in some sense, it doesn't matter because a lot of times, you're going to let MATLAB or whatever computer program you're doing handle most of those calculations for you. Okay. Are there any final questions on this example right here? Okay. Okay, so we have a bit of time left, so I do want to go start kind of the next big topic here, which is our next shape, which is our 4-node quadrilateral. Okay. And so our 4-node quadrilateral is the other 2D shape that's often used in finite elements. Okay. Okay. And so it looks something like this. Okay. And so the way we number this is like the following. Okay. So we usually start in the bottom left and we go around like that. And so just like we saw in the triangle, each of these nodes here will have their own coordinates. And so we'll have x1, y1. Then we have x2, y2. Okay. We have x3, y3. Okay. And then we have x4, y4. Okay. Okay. And so since we have 4 nodes here, what this means is that we're going to have 4 shape functions. Okay. So remember, we usually have 1 shape function per node. Okay. And so what this also means is that our interpolation function will also have an extra term. Okay. Okay, so let's write out the interpolation function here. Okay. And so our interpolation function, okay, is still going to be t as a function of x and y. Okay. Okay. And so here I have our four constants. Okay. And so just like before, I'm going to make the first constant our linear term in x, and our second term, or second constant, a2, to be a linear term in y. That's addition to our constant term, a0, okay? But then now the question is, what do we put in for the last term there, okay? And so a3 can't be a constant because a0 is already a constant here, okay? And remember, what we want is we want our shape functions here to be linear, okay? And so we can't put an x squared right there because an x squared, that's a quadratic term, and we can't put a y squared right there either because that's also a quadratic term. Okay. Oops. And so what we can do instead is we can do kind of like a pseudo quadratic, pseudo linear term. Okay. And so what we're going to have instead is x times y. And so technically it's a quadratic term because we're multiplying two independent variables, but it's also technically linear because we just have x in the first order and y to the first order. Okay. Okay. Any questions on this? Okay. So we'll pick this up on Wednesday. So Wednesday, I'll have the project specs and all the starter codes ready for you. So we'll start the lecture talking about that, and then after that, we'll pick up this lecture basically right here. Okay. So thank you everybody for tuning in today. Hope everyone's does well this week, and have a good evening. And I'll see you guys on Wednesday.
Thank you, Professor.
Thanks, guys. Yeah. So if you downloaded MATLAB with all the bells and whistles already, I think the toolbox is called the PDE toolbox. Okay, so it looks like this. Yeah. Yeah, and you can ask some questions regarding the last one too. But if you if you want to, Chris, if you want to check your MATLAB and see if you have the PDE toolbox, then that's where the meshing software is. Yep. Mm-hmm. All right, Stephen. So go ahead. If you want to ask some questions. Yes, yeah. So when you're doing weak form approximate solutions, then the solution is dependent on what form that you choose. And so if you assume a linear function, then you're going to get one solution for the problem. But if you assume a quadratic function, then you're going to get another function. But there is a caveat for this. So actually, I gave you one of those special cases in the homework. And so I think in problem 3A, I asked you to redo problem 2A. There, okay. What I asked you to assume was that I asked you to assume that's a quadratic function. But that problem was actually very unique because when you solve that problem with the strong form, what you found was that the solution was already a linear function. Okay? And so if you try to assume that the solution is a quadratic function, what you probably should have found was that the quadratic term was equal to 0 there. So whatever coefficient that you put there. So I think it was A2 on that. And so what you should have found was that A2 was equal to 0, and what you end up with is the exact same solution that you chose before, yeah, for the strong. But yeah, so depending on what you assume the solution form to be, that's going to change your solution. You can even do something really exotic, like you can even assume that the solution is like a sinusoidal function, so it's like a sine or a cosine, and that's gonna change your result as well. Is there specific conditions that require to use the weak form method? I think the best way to use the weak form is to basically just make sure that your any derivatives that you have in your problem are balanced as much as you can. And so we're working with mostly second order terms. So if you can balance those derivatives, that's good. Yes, yes. And so the weak form, actually, the fact that we can find an approximate solution is actually a strength of that. And so for 1D, it's kind of pointless because in 1D problems you can solve for the exact solution and it's not that big a deal. But for 2D problems, if we had our 2D heat equation, which basically looks like this, right? If our 2D heat equation looks something like that, it's a lot more difficult to find the solution, right? So you might be able to find the solution if your domain was something simple like a square. And so, if your domain was simple, you can do that. But then what if your domain looks something like this? Right? And so if you try to solve this equation on this kind of really complicated domain, you can do it eventually, but it's going to be, really, really difficult to do that. And so the fact that we can solve for an approximate solution on a really complicated domain like this is actually faster than trying to solve for an exact solution on a really complicated domain. Yeah. And if you satisfy certain conditions for your assumed solution, which the finite element form tends to do, you get something that's, you know, not quite exact, but something that's really, really, really close. Especially if you refine your mesh quite a bit. So if you have a really refined mesh, then your weak form solution is basically going to be right on top of your exact solution. Yeah, yeah. And so you're right. So in the cases where you can find an exact solution, that's the preferable way to solve it. But for cases where you can't find an exact solution, then this approximate method actually saves you a ton of work. Exactly, right. So when in the case when you don't have a straightforward domain, then the weak form is very superior. And so in 1D, you don't really see that, because in 1D, you know, there's only one type of domain you can have, which is a line. And the other type of domain you can have is a shorter line. So, you know, in 1D, there's no way to get any complicated geometries. But in 2D, you know, you can get some really exotic geometries. And in 3D, it gets even worse. So in 3D, you can get, you know, all different kinds of geometries. Yeah. Yep. Mm-hmm. Yeah, great questions. Yeah, of course. Yeah, always happy to answer. Yep, see you. Hassan, did you have any more questions? Okay. So if you don't have any more questions, I'm going to close the session for today, and the recording should be up pretty soon. Okay. So have a good evening, and I'll see you on Wednesday.